طيب طيب بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Welcome everyone to the topic number 4. So hope you had a great break. Assume you didn't hear that from me before. Okay, so now let's work on the stability. Continue with the stability of dynamical system. Yeah, let me do it. Okay. Let's start with a recap as usual. So we're considering dynamical systems written in the standard state space form for nonlinear systems in this form. X dot is equal to f of x plus g of x u, and y is equal to some h of x. And this is the state space model for the dynamical system. And we're focusing on analyzing the stability of systems of this form. X dot is equal to f of x. And this can correspond to two things. This can correspond either to the open loop system. So you say, I don't have any inputs. I just want to understand how the system works by itself, how it evolves by itself without any inputs. Or it can include that you already chose a control law and you plugged it in, and you're talking about the closed loop dynamical systems. In both cases, okay, the tools that we're talking about in terms of stability of dynamical systems are being used. In the first case, you understand the stability of a system by itself. In the second case, you're understanding how your controller that you designed is affecting the system together. Okay, so if this is a drone, if this is the model of the drone and these are the inputs, the thrusts of the propellers, then in the end you're talking about the system with the controller. How does it behave? How does it fly? Okay. We looked at a bunch of mechanical systems, and we saw that there's this recurrent theme that the state space is given by some tangent bundle. In the case of the mass spring damper system, it's just a scalar system in R2. The simple pendulum, we had this manifold, which is the tangent bundle of the one sphere. The N-link manipulator, we have the tangent bundle of some N torus if you have revolute joints, as we saw before. The satellite, which is simply the tangent bundle of SO3, or if you have a UAV, which is not only rotating but also translating, then you have the tangent bundle of SE3. Okay, and all of these systems, all of these mechanical systems, they have this geometric structure underlying, and then how can we design controllers that respect the structure? So this is what we're aiming for. And then we looked at the nature of x dot is equal to f of x as an ODE. And we said that if you only look at it from an Rn perspective, then f, you think of it as a map from Rn to Rn. It's just I don't know, multivariable matrix, if you want to think of it this way. But actually, if you look at it from the non-Euclidean space, you see clearly that f is a map that attaches to every point on the manifold in the state space of tangent vector. And we said that this is equivalent to defining a vector field on the state space. So if the state space has the shape of a paraboloid, then the f of x defines this vector field that you see here in terms of arrows. And the integral curves of the system are simply how it will evolve with time. So if you start with some initial condition here, it will follow the integral curve of this vector field that is defined by x dot is equal to f of x. Equilibrium points. So when we talked, again, just as a repetition, when you talk about equilibrium points, you never talk about equilibrium points of a linear system, because a linear system always has the origin as the equilibrium point. And it has only one equilibrium point. When you have nonlinear systems, you have multiple equilibrium points. So you need to talk about each of them separately. All of these equilibrium points, they satisfy f of x equal to 0. So they are roots of the dynamical equations. In other words, they are vectors that have x dot is equal to 0. So you go to that point and you don't move anymore. And then when you are talking about the equilibrium point of one of these, if you're talking about one of the equilibrium points of the system, you can either categorize it as being stable, unstable, locally asymptotically stable, or globally asymptotically stable. There are more stronger notions of stability, like exponential stability, but we're not going to be going there. These are enough. So something that is unstable means that if you start near this equilibrium point, you will always go away from it. If you're stable, this means that if you start near it, you will always stay near it. If you're locally asymptotically stable, it means that there is some region, if you start near this equilibrium point, eventually you will go to it, you will converge to that point. If you're globally asymptotically stable, this means that if you start anywhere in the state space, you're going to converge to this equilibrium point. So this is the strongest thing that this is the strongest notion of stability that you can have. To be global, of course, the asymptotic part depends on how it means as time goes to infinity. There are more stronger notions, for example, to be global exponentially stable. I think this is the strongest one that you can have. We looked at the equilibrium points of the pendulum last time. We said, okay, these are the equations of the of motion of the pendulum written in state space form, where x1 is equal to theta and x2 is equal to theta dot. We said that we showed that we have two positions, one which is the downward position and one which is the upward position. These are the two equilibrium points. We derived them by solving x1 dot is equal to 0 and x2 dot is equal to 0. So the first one says x2 is equal to 0, and the second one says that sine of x1 is equal to 0. And inside of this region from minus pi to pi, then you have only that x1 is equal to 0, x1 is equal to pi, which is the downward position not moving and the upward position not moving. Intuitively, okay, again, if you just visualize it, then if I start with the pendulum downwards and if I give it some perturbation, if I start next to it, then you'll find that, okay, if there's friction, of course, then it will start to stop. Okay, so this is the evolution of the system. You can visualize it. If you start from the upward direction and then you give it a little bit of a jump, it will always move away from this point. So intuitively, we know that the upward position is unstable, while the downward position or the downward equilibrium point is locally asymptotically stable. The question what we want to do now is how can we visualize? How can we prove, just given this system, that these equilibrium points have these stability notions? What we did last time is we looked at the phase portrait of this. This is one visual way that you can do it, but it's only limited to one-dimensional mechanical systems because you can only draw in 2D this vector field, and that's it. But now what we want to do is we want to use some analytical methods to try to talk about the stability, not just some visual methods, and definitely not solving the system. So we're not interested in solving the system or numerically solving solving the differential equations to say how the stability of the equilibrium points look like. So Lyapunov has a lot of work. He's the most famous person in this area and the stability of dynamical systems. And he had a lot of work. One of the most famous is his indirect method, which is usually not actually attributed to him because it's very simple. It relies on trying to linearize the system, while the second one is based on, again, trying to find some energy-like function to try to analyze the properties of this function. And then we can infer properties of this equilibrium points. And we're going to be talking today about these two methods today, inshallah. Last time we talked about the Lyapunov's indirect method. So we say that x dot is equal to f of x. It has some equilibrium point or points, x star. Then we linearize the system, this nonlinear system. We linearize it around each of these equilibrium points. We get linear systems of this form. Z dot is equal to a z. Each one of these z's is a perturbation from this equilibrium point. So if you're starting around, so z here is x minus x star. So if x star is for example, in the case of the pendulum, is the downward position, then z would be perturbations from this location, while if you're looking at the upward position, then z would be perturbations from the upward position. So this is what the z is. It's just small changes from the equilibrium points. While the A is equivalent to the Jacobian evaluated at the equilibrium point. And the Jacobian we introduced it last time in a differential, in a geometric manner, but in the end, it's just what you're all familiar with, which is taking the partial derivative of each of these functions with respect to the state variables. And Lyapunov's indirect method or the linearization method is very simple. You compute the eigenvalues, which in the end, we have A here will be an n by n matrix. So you're going to have n eigenvalues. Each one of them is a complex number. And you took a look at the real part. Only the real part you can deduce from it the stability. The real part, if only one of them has a real part that's positive, we conclude that the equilibrium point is unstable, not only for the linear system, but also for the nonlinear system. And this is the power of Lyapunov's indirect method, that we're using a linearized version, which is an approximation of the original system, to try to deduce properties of the nonlinear system. Those? No. You're late. Okay. If one of these eigenvalues is equal to 0, if only one of them is equal to 0, then we cannot conclude anything. Of course, here, if one of them is equal to 0, and you don't have anything that is more than 0. Okay, so here it suffices to only have one of them greater than 0 to conclude that it's unstable. If you want to conclude stability or asymptotic stability using this method, then you need to have the real part of all of the eigenvalues less than 0, strictly less than 0. So you shouldn't have any eigenvalues with the real part on the imaginary axis. Okay. What does it mean that the Lyapunov method is inconclusive? What does that mean? Does it mean that the system is unstable or stable? We don't know exactly. The method cannot tell us. The method cannot conclude anything about the stability. So you should look at higher order methods. So the first thing you try indirect method of Lyapunov. If it works, if you can conclude something, then good. If not, then you look at other methods. Okay. So this is usually the drill. Now let's look at some examples of this. Okay. You can also have a lot of examples at home, toy problems to play around with, inshallah, in the homework and in the assignment. So this is the pendulum dynamics, but with the Jacobian matrix of it. So again, just to remind you that this is the pendulum dynamics written down there, and this is the Jacobian here, which is just the partial derivatives of these two functions, f1 and f2, with respect to x1 and x2. C1 and C2 are simply will be the constants, which are the G over L and the B over ML squared. We're just gonna call them constants now. Okay. This Jacobian, if you plug in the equilibrium point, which is the first one, which is 0, 0, you're gonna get this matrix. If you plug in the pi and 0, you're gonna get this matrix. Okay. So this is the linearized system around the downward position, and this is the linearized system around the top position. The question is, which one of these is stable and which one is unstable? Can we look at these matrices and derive the eigenvalues and see whether they are positive or negative? How do you calculate the eigenvalues? The determinant of what? Of some variable lambda multiplied by the identity minus this matrix, and then you solve this characteristic equation, right? MATLAB does it for you, Eig of the matrix. It even does it symbolically. I'm going to be putting a MATLAB code that you can see how to do it if you don't know. What you see here is I'm going to be plotting the real value of these eigenvalues. So how many eigenvalues do we have here? Let's go back a little bit. We have 2 for each. So we have 2 for A1 and 2 for A2, right? I'm going to only look at the real part. If you find that the real part of the two real parts, so the real part of the two eigenvalues for A1 are always negative for all C1 and C2, this means what? It is always stable, no matter what the value of C1 and C2 is. This is exactly what this plot says. So what you see here are contour plots, which is because this is so we have C1 and C2. So C1 is the horizontal axis, C2 is the vertical axis. All of these contours are the real value of the first eigenvalue for A1. So this is the real of lambda 1. This is the real of lambda 2 for A1. What do you see here in all of these values? What? They're always negative, exactly. So if you have, for example, if you choose C1 to be 1 and C2 to be 1, you get a value of minus 0.5 for the eigenvalue. And if you choose C1 to be 1 and C2 to be 1, you also get minus 0.5. So minus 0.5 and minus 0.5 for the two eigenvalues of A1. Again, choose C1 to be 2, C2 to be 2.5, let's see, something in between, you get minus 1.5, and so on and so forth. Okay, so this is what these contour plots mean. Okay, because we want to calculate the eigenvalues for all possible values of the C1 and the C2, and if you go back, the C1 and the C2 are simply all of the ratios, all of the values that B, M, L squared, and G and L can take. Okay. We're assuming here, again, B is the damping coefficient. Is it positive or negative value? Always positive. What about the mass? Always positive. L squared, always positive. So in the end, C2 is always a positive number. What about the G? Positive number. What about the L? positive number. So G over L is always a positive number. That's why in this plot, we're only plotting greater C1 to be positive and C2 to be positive. Okay. So this is a very nice way that you can check for all values at once. So with this, we can conclude that the real value of the eigenvalues of A1 are always negative, which means that we can conclude that X1 star, which is the 0, 0, the downward position for the pendulum, is locally asymptotically stable. What about the A2? Check it out for yourself. So this is the real value of lambda 1, and this is the real value of lambda 2 for the second linearized system. What do you see? Lambda 2 always has positive values. For the same C1 and C2, so if I choose, for example, C1 to be 1 and C2 to be 1.5, I get 0.5 as the eigenvalue. And if I do the same here, I get, I don't know, somewhere between minus 1.5. So you see one of the eigenvalues is negative, but the other one is positive. What does that mean? It means that the second system is unstable, which means that the top position for the pendulum is an unstable equilibrium point. Okay, so you see, this is how we do it in practice. Okay, another example. This is a very interesting example. Again, it's a very classical one, and it also has some nice. It's actually you can really go way further than just trying out with the Lyapunov's indirect method. But again, this is a very nice example. So pay attention to this, please. We're going to look at the rotational dynamics, okay, of a rigid body, but only the rotational part. So there is no translation. So this is just a rigid body that's rotating in its place, which is a simple model for a satellite. What a satellite does is that it doesn't fall, it doesn't move. Assume it doesn't move. So we're only looking at the dynamics of it while rotating. We're going to assume that J1 and J2 and J3 are around the moments of inertia around the principal axis. So we're going to assume that what you see there are in black, which is the body fixed frame, is the principal axis, which means that J expressed in this frame is a diagonal matrix, and omega 1 and omega 2 and omega 3 are rotations around these three axes. Okay. The rotational dynamics is given by that, so you've seen it several times before. We're going to simplifying a little bit. We don't have any torques, so we're not applying any torques here. We're looking at the open loop system. This equation is very interesting because if you look at the second equation, which is the momentum balance, the conservation of momentum equation, you see it doesn't depend on what? The rotation matrix, exactly. The rotation matrix depends on omega, but the omega dynamics doesn't depend on rotation matrix, which means that omega can be solved by itself. It's an equation only in omega. It's a differential equation only on omega. And after you know omega, you can integrate it to get the R. Okay, so this is known as something called reduction, right? So we already have a natural, we have a natural symmetry in the system here, in the sense that we can solve this differential equation. These are two differential equations, but we can solve the first one, right, as the first stage, and then we can solve the second one as the second stage. We don't need to solve them both together. So this is exactly what we're going to be we're going to be doing here. We're going to be looking only at the second equation, the momentum balance, and we can write it like this. So J is a diagonal matrix. Again, this is a homework for you to try to test it for yourself. It's very easy to look at it. J inverse gives you these three terms in the denominator. J omega gives you, again, these terms, and we have here the cross product, which in the end gives this, okay, this coupling between omega 1 and omega 2 and omega 3. Omega 1 dot relies only on omega 2 and omega 3 non-linearly. Omega 2 dot on 1 and 3 non-linearly. Omega 3 dot on 1 and 2 linearly. So this is the gyroscopic effects. An equilibrium point for this dynamical system is one that satisfies omega 1 dot equal to 0, omega 2 dot equal to 0, omega 3 dot equal to 0. Okay. So substitute that. How many equilibrium points do you think this system has? 3. What are they? No, the equilibrium points have nothing to do with the eigenvalues. The equilibrium point are simply all of the points that satisfy x dot is equal to f of x, and then f of x is equal to 0. So you only look at the system without talking about the stability. What? One equilibrium point, what is it? 0, 0, 0, right? So if I substitute this to be 0 and this to be 0, I get that whatever the solution of these three equations together means that omega 1 is equal to 0, omega 2 is equal to 0, and omega 3 is equal to 0. That's correct, but incomplete. There are three more equilibrium points. Each of them to be 0 and others are not 0. Not correct. Almost there. You have four equilibrium points. You have the trivial equilibrium point that you all mentioned. The three angular velocities are 0, which means that this satellite or this rigid body is not rotating at all. You have spinning around the first axis. Okay, so for example, if this is the rigid body we're talking about, okay, so and if these are the three axes, okay, so I can rotate around this axis, I can rotate around this axis, and I can rotate around this axis. So these are the three axes, the principal axes. If the rigid body is doing nothing but just this rotation, okay, then it's also an equilibrium point, right? So if omega 1 is a constant value, right, is constantly rotating, not with any acceleration, so it's just a constant angular velocity, while the other two are 0, this will satisfy that this is an equilibrium point. You can also have that you're rotating around the second axis only. This is also another equilibrium point. You can have also that you're rotating around the third axis only, and then you also get an equilibrium point. So we have four equilibrium points. One of them is the trivial one, right, which is the body is not rotating. The other three are you have a constant rotation around one of the three principal axes. Is that clear? Two motions. We're only considering one motion at the same time. Because this is just the solution. You can try it out for yourself. If you say that omega 1 and omega 2 at the same time are non-zero, right? Then omega 1 and omega 2 are non-zero, then this becomes not 0. This becomes 0 and this becomes 0. So you don't satisfy 0, 0, 0. You see? You need to have only two, you need to have two of them to be 0 and the third one non-zero for this to satisfy. This is why these are the only four possible solutions. Okay. Now let's look at the stability. What we're going to be doing is something very interesting. We're going to be assuming that J1 and J2 and J3 are ordered. Okay? So we're going to assume that J1 is bigger than J2 and bigger than J3. Okay? This is just an assumption, which means that these equations, we can rewrite them simply by three constants, where C1 and C3 are bigger than 0 and C2 is less than 0. Check it out for yourself. Okay. So if J1 is bigger than J2, then this is a positive value. So C3 is positive. If J2 is bigger than J3, then this is a positive value. If J1 is bigger than J3, then we have here a negative value. Okay. So it means that, you see, we have a clear separation between the biggest axis, between rotation around the biggest axis. Let's assume that this is rotation around the biggest axis, and this is rotation around the smallest axis, while the intermediate axis, the one in between, okay, which is the rotation around the intermediate axis, will have a minus sign. Can we conclude that this is unstable and this is stable and this is stable immediately? You cannot say anything, right? So don't do that, okay, mistake. It's not because this is positive and this is negative and this is positive, then we can say anything, right? This is still a nonlinear system. So how can we test its stability? Let's try Lyapunov's indirect method first and see what do we get. Yeah. Okay. So this is how the Jacobian looks like. Again, three equations. Okay, we will differentiate around. We differentiate with respect to omega 1, omega 2, omega 3, and it's very important. Again, if you don't know that, but if you know it, it's trivial. But if you don't, just a precaution. The Jacobian, we don't plug in anything. So the Jacobian is also a function of x, or a function of omega in general, a function of x in general, a function of omega in this example. So this is how the Jacobian looks like. Okay? Just simply taking the partial derivatives of these three equations with respect to the three variables that you have. Okay, you can test it out, you can check it for yourself at home. Now let's plug in. So this is where we plug in the equilibrium points because we want to test the stability of the 4 equilibrium points. We're going to plug in here the equilibrium point omega star A, which was the 0, 0, 0. This is the omega star B, which was capital omega in the first, around the first axis, and 0, 0. This is 0 capital omega 0, and this is 0, 0 capital omega. And we get these 4 dynamical systems. And then what do you do next? Calculate the eigenvalues. Again, we're going to leave everything symbolically. So we're not going to substitute anything. Okay, no numbers, just leave it symbolically. The eigenvalues of this one will be 0, 0, and 0. It's a 0 matrix, so it has 3 eigenvalues. This is a skew-symmetric matrix. It has 1 0 eigenvalue, and 2 of them that have the square root of C2 and C3. Okay, the square root of C2 and C3. This one, again, one of them is 0. And we have the square root of C1 and C3. This one is one of them is 0, and we have the square root of C1 and C2. Okay, so this is what the just following blindly the method tells us. Now let's try to analyze C1 and C2 and C3. What did we assume that they have? What are their signs? We assume C1 and C3 to be, and C2. Let's try this one first. So C2 and C3. One of them is negative, one of them is positive. Their product is negative. So this is a square root of a negative value, and this is a square root of a negative value. What do we get? An imaginary number. And this imaginary number will be positive, this imaginary number will be negative, and they will be exactly the same number, right? So in the end, what does lambda 2 and lambda 3 correspond to? Complex conjugate, exactly. They are 2 complex conjugate eigenvalues of each other. So this is of this one. So in the end, the real part of all of these 3 eigenvalues, where does it lie? On the imaginary axis. Can we conclude anything about it from Lyapunov's indirect method? No, because we have 3 eigenvalues that are in the imaginary. Cannot say anything. What about this one? Same. 3 eigenvalues with the 0 real part. We cannot say anything. What about this one? C1 and C2. One of them is positive, one of them is negative. Their product is negative. The same happens for it. And again, remember that this was the rotation around the big axis. This was the rotation around the small axis. This is rotation about the intermediate axis. You have the square root of C1 and C2. Sorry, C1 and C3. C1 and C3 are both. The square root of them is positive. So it's real. So there's no imaginary numbers. So in the end, what do we have here? We have one eigenvalue that's 0, another eigenvalue that is positive, and another eigenvalue that is, what do we conclude about the stability? It's unstable. So in the end, we conclude that the first equilibrium point is, we cannot say anything. It's inconclusive. The method is inconclusive. The second one, the method is inconclusive. The last one, the method is inconclusive. But the third one, which is the interesting result, it's unstable. And this is very interesting by itself. Okay? Even though we couldn't say anything about the remaining 3, but knowing only from Lyapunov's indirect method that this stability, this equilibrium point is unstable is very interesting. You can show, but not with Lyapunov's indirect method, that this one is actually stable, okay, asymptotically stable, and this one is asymptotically stable, while this one is only stable, okay, marginally stable. Okay, let me go back to it, okay? I need to go back to it. And actually, we're going to be doing it later, inshallah. What? Yeah. It's not, no. I'm not saying it's unstable. Why? That's right, but this is a nonlinear system, right? We're looking at perturbations around the place where the system is not moving, okay? I would guess it's stable, right? You move around it, but again, you just don't converge to it. Okay, that's my guess. Okay. Now let me show you a demo of this. Actually, this is not math. This is real life. Okay, I'm gonna show you a real experiment to show you that this is really true. Okay, I don't know if you've seen something like this before. So this is the satellite we're gonna talk about. Okay, unfortunately, I don't have zero gravity here, so we're gonna have to do this experiment in gravity, and you have to visualize that. Okay, this will be falling on forever. or we're going to be going up, and then this will not move. Okay. My PhD supervisor was lucky enough to actually to do a zero gravity experiment, and he actually did this experiment, and he has a videotape. Okay, if you're interested, I can share it with you. So this is a book, okay, and it's a simple. Again, let's go back. It's the physical system that we're talking about here. Okay, we want to study the stability of it rotating around this axis. Okay. And rotating around this axis, and rotating around this axis, okay? So these are three different axes. How do we know the biggest one from the smallest one? Take a look at this. So this is the biggest area that we have, right? Again, so this is just a cuboid. So this is the smallest area. This is the intermediate area, and this is the biggest area, right? So rotation around this axis, okay, is stable. Rotation around this axis, which is the smallest one, is stable, while rotation around the intermediate axis, which is this one, is unstable. Unstable means that no matter how hard we try to kickstart the system, it will never do this rotation, right? It will always go away from it. While this rotation is stable, what does it mean? It means that if it has some perturbation, it will always go back to it. The same also for that one. If we kickstart the system to make it rotate like this, and then it diverges from this rotation, it will always go back to it. This is what the stability means. Now, hope this works. The first one is trivial, okay? A kid can do it, okay? Just this rotation, okay? So this is rotation around the biggest axis, okay? If you kickstart it, of course, because it's falling now, I have to hold it. But if you imagine that this is a satellite, and you just give it a push like this, it will always keep on rotating like this. Nothing will stop it, okay? So again, see? It's always stable. It's always rotating around this axis. The same also for this, around this axis, okay? Let's see. Let's see how to do it. I think it's, yeah, this one. You see? Now check this one. I'm going to rotate around the intermediate axis now. Again, you have it on tape. You can do it very slow motion again, but check out what will happen. It can never maintain this rotation and come back down. You'll always find there's some wobbling that will happen because it's unstable equilibrium point. You see? Okay. So again, try to do it at home. Okay. Use something that you can dispose of. Don't use your tablet or your phones. So, yeah, question. This one? Yes. J1, let's see. J1 is equal to omega 2. J1 is equal to J2. Then, let's see. So let's try it out. So this will be 0. And omega, yeah, that's right. Yeah, in this case, actually, you have more equilibrium points. Yeah, that's right. That's right. If given that J1 is equal to J2, precisely equal to, mathematically, right? But again, from a mathematical perspective, yes, you have now more equilibrium points. Okay, I think now it will. We already in this way we already have infinite equilibrium points, by the way, because omega here can be any number, right? So omega here can be any number from minus r to r. Okay, so we already had we had 4 physically different equilibrium points, but technically we have an infinite number of here. So you just increase the number of infinite values that you have. Yes, that's true.
The assumption we have made about the J, is it trivial? We can do this and get an equilibrium points according to it. I mean, we did the assumption. Is it right, or it doesn't need to be?
It depends on the system you're talking about. For example, this book, it has the 3 principal axes just because of the way it's constructed. It has the 3 ones, the 3 J's. They are bigger. They are not equal, and they are ordered. You see, because this is the biggest area. This is the small. This is the smallest one, and this is the intermediate one.
So it's to this specific system.
Exactly. Yeah. Exactly. Yeah. We're just trying to again. So we're trying to take the system, trying to make it into a form that we can apply on it the method to see what will happen. Right. That's the idea.
Second point about saying the other zeros or so are stable.
Yeah.
So here they will be stable using, for example,
another method. That's exactly. I haven't showed it yet. Exactly. I haven't showed it yet. I only showed it to you by solving the system, by solving the differential equation, by making the system evolve, but I haven't showed you how to do it mathematically yet, or by analyzing the system. Yes, you're true. Any more questions? Okay. Let's see how much time we have. Okay. Now let's go to, so this is Lyapunov's indirect method. Again, very simple to apply. Okay. And you can conclude either the local asymptotic stability or the instability of some equilibrium points. But Lyapunov's direct method is more general. First of all, who I never heard about it before? Lyapunov's direct method. 1, 2, 4. The rest know it. Nonlinear systems course, nonlinear control, adaptive control. Okay, so bear with me if this is repeated stuff. We're gonna be only using it for this lecture. Who's familiar with Lassalle's invariance principle? The invariant set theorem. What? Been a long time, but no one? Okay, good. So hopefully you're going to learn something new today. So first we need, before talking about what Lyapunov's direct method is, let's talk about what a positive definite function is. So assume x is just a scalar. So here we're talking about a scalar function. So v of x is called, or we say that it's a positive definite function if v of the origin is equal to 0, right? And v of x is greater than 0 for all x that's not equal to 0, okay? Which means that it has this shape, right? It means that it's just like a parabola. So v of x equal to x squared, so just as an example, is an example of a positive definite function. This is also another example of a positive definite function, right? You see, because at 0, we have that the function is 0, and around from 0, right, we have it's positive, okay? This is the shape, sorry, there was something missing here. So v2, this is the shape of the other function. So this is v1 of x equal to x squared, and this is x squared minus some x to the power of 4 term. This one, again, is v of 0 is equal to 0, and v of x is greater than 0 for all values of x. So we say that this is a positive definite function, but globally, everywhere it satisfies that. However, the other one is greater than x, but up to some limits, right? And these limits are precisely this point and that point, right? So only in the region where the x is less than or is greater than or equal is greater than minus 2.77 or less than 2.77, then we have that this is a positive definite function. Other than that, it's not. Okay. So this is a locally positive definite function, while this is a globally positive definite function. Okay. This is just how visually it looks like for scalar functions. This is how it looks like for, again, for a function of two variables, right? x1 and x2. Again, the parabola just extends everywhere. And this is the same function that we're talking about, but it's a function of x1 and x2. And again, you can, of course, generalize this to k-dimensional vectors or variables. But again, you cannot visualize it anymore. But the same idea holds. There's a lot of, okay. So Lyapunov's direct method says the following. Okay. First, we will not linearize. We will work directly with the nonlinear system. So we're going to work directly with x dot is equal to f of x. X star is an equilibrium point of the system. And we say that x star is a stable equilibrium point if you can satisfy the following conditions. The first one is to find the Lyapunov function. Okay. What is the Lyapunov function? It's just the name for a function of x that will satisfy these conditions. First of all, v at the equilibrium point is equal to 0. V of x is greater than 0, which means it's a positive definite function. But also, you need to check how v changes along the trajectories of the system, which means that v dot of x should be less than or equal to 0. Less than or equal to 0 means that this is a negative semi-definite function. This is just a terminology. So if v of x is greater than 0, we say it's a positive definite function. If v of x is less than or equal to 0, then we say it's a negative semi-definite function. And I'm going to show you how can we check later on with some examples. If you can find the Lyapunov function, and this is the point. Lyapunov's method tells you if you find a function and it satisfies these conditions, then you can conclude that the origin or the equilibrium point of the original system of the nonlinear system is stable. It doesn't tell you how to find it. It tells you only this is the method. If you can get the Lyapunov function that is not only negative semi-definite but strictly negative definite, you can conclude that the system is asymptotically stable. If you have these two conditions, and you can also have a third one, that you can guarantee that v of x is readily unbounded. Readily unbounded means that if you go any direction to infinity, if you go to any direction away from the equilibrium point to infinity, you're going to find that v tends to infinity. Okay, so this is a globally positive definite function, which means that you have a positive definite globally positive definite Lyapunov function. And it's also strictly negative definite. If you find these conditions, then you can guarantee global asymptotic stability. Okay? This is mathematically what the theorem says. Apply it in practice means that you need to find, of course, what the Lyapunov function is. First of all, again, what do you think the idea of this equation, this Lyapunov function, or this Lyapunov theory is? Where did Lyapunov get this idea from? From energy, exactly. Energy is a scalar quantity of the systems that we have. So I might have a mechanical system, which is the pendulum, or the mass spring damper system, or the N-link manipulator, or the floating base manipulator, or the MAV, whatever. All of these systems, because they are mechanical systems, they have two types of energy. What are they? Kinetic energy and potential energy. When the energy converges to 0, what does that mean? What does it mean physically? If I tell you that the kinetic energy of a system is 0, it means it's not moving, right? It's stable. It's stopped. It's not doing any motion anymore. This is what the kinetic energy means. So this is the idea that Lyapunov came from. But he generalized it not only working with energy function, but working with any other energy-like function that you can find. And if you can satisfy the same conditions that a mechanical system would behave around with this energy, with this mechanical energy, then you can conclude the stability of the equilibrium point. Okay? Because we want to talk about a certain equilibrium point, this is where the v of x star is equal to 0 comes into place. So this is why we need it to be a minimum. We need it to be a root. We need the x star, which is the equilibrium point of the original system we're talking about. We need it also to be a root of the system here. Okay? So any questions before we move on? So you're raising your hand. Because this is enough. The second derivative, we're going to go to it when this method fails. We're gonna come to that later, inshallah. Okay. But the first derivative only works. Okay. So I'm not going to show you now examples of how Lyapunov theory works. If you never did it before, again, you need just to work it out yourself. It's very easy. However, it's inconclusive in a lot of cases. Okay. It has a very big limitation. Okay. And I'm going to show you now in practice, or I'm just going to show you in the example now that we already had, what this limitation is. Take the pendulum example, the same one we're working with. And what I did here is just I put all of the values to be 0. I put the C1 and the C2, sorry, the C1 and the C2 to be 1, okay, just for simplicity. That's why it looks very nice. The system. I'm going to choose this Lyapunov function. What does it look like to you? This first term is kinetic energy. It's half J, it's supposed to be half ml squared theta dot squared, right? If you have just a pendulum in the end, right? So this is the kinetic energy of the pendulum. I chose here ml squared to be 1. This is why it looks like that. And then what do we have here for the potential energy? Because we have some gravity here. So what is this term, do you think? is supposed to be mgl, right? 1 minus cosine theta, right? Because it's mg, it's like talking about the mg, you have mg multiplied by the height, and the height of the pendulum is the length multiplied by 1 minus cosine theta. Okay? If you ever did it before, okay, then you know it. If not, it's very easy to prove it for yourself. That this is the potential energy for the case that we have the parameters are equal to 1. So this is the function that we're going to be starting with, which is thus the energy. Is the first guess you'll always start with. I have a mechanical system. The best thing to start with is the total energy. And let's see whether we can use it as a Lyapunov function. First of all, is it positive definite? How do you know that? Let's take the first term alone. This is what? Just a parabola, right? So in the theta dot direction, okay, it's always positive. What about this term? Cosine theta is always between minus 1 and 1. So if you have a value that's minus 1, you get 1 minus minus 1, you get 2. If you're on the other side, you get a value of 1, you get 1 minus 1, which is equal to 0, and this is still positive, so you have sure that this is always a positive definite function. Let's look at when we plug in the equilibrium points, which are x1 is equal to 0 and x2 is equal to 0, or theta is equal to 0 and theta dot is equal to 0. Theta 1 is equal to 0. Sorry, theta is equal to 0 means the cosine of theta 0 is equal to 1. So 1 minus 1 is 0. Theta dot is equal to 0 means this is 0. So we have that v is 0 and 0 at the downward position. At the upward position, which is pi and 0, this is still 0. And this is cosine pi, which is negative 1, right? So we have 1 minus minus 1. It's 2. Is it 0? No. Can we solve that problem? It's very trivial to solve. I can change the Lyapunov function to be what? No, it's easier than that. Minus 2. I can always shift the Lyapunov function, right? I know that v of x star, in this case, will give me 2, right? So I can just add here minus 2, and it's just a constant. When I take the differentiation, it will disappear. Right? And this is a very nice trick that we can always shift the Lyapunov function by any constant, just to make sure that we get the value to be equal to 0. Okay? So this is just a trick that we can always do. In either case, let's start with this Lyapunov function. Let's look at what the v dot looks like. What do you do here? You take the partial derivative of this term with respect to theta dot and multiply it by theta double dot. You take the partial derivative of this one with respect to theta, and then you multiply it by theta dot, which is these two terms. Okay. Now substitute theta double dot from this equation. Remember that this second equation was originally theta double dot. The reason I keep it here with theta and theta dot is that I want to show you what the variables are. Okay, just not to hide them with x1 and x2. In the end, we get minus theta dot squared, which is equivalent that v dot is equal to minus x2 squared. Is it negative definite? Is it always a negative function? Is it always a negative function? What? Exactly. It's always 0 when theta dot is equal to 0. That's true. But what about theta? It can be 0. V dot can be equal to 0 without theta being equal to 0. Because you only get here theta dot. Is that clear? No? Again? So v dot, okay, is equal to minus theta dot squared. Okay. What are the values of x? And x here is x1 and x2, which is theta and theta dot. What are the values of x that would make v dot is equal to 0? Is theta dot equal to 0 and theta equal? No. Theta equal to anything, exactly. Theta can be any value and then you can get theta dot, and with only theta dot is equal to 0, you can make the v dot is equal to 0. How did we derive this? So this one, theta dot multiplied by minus theta dot. So theta dot minus theta dot. Okay? And theta dot minus sine theta. And you have outside there is theta dot plus sine theta. And then you get this term. Okay? So you see what happens? This function is always less than or equal 0. Right? So this is a negative semi-definite function. It's not a negative definite function. So this is the type of function that we say it's a negative semi-definite, not negative definite. For it to be negative definite, one of the conditions for it to be negative definite, it means that it should be 0 when x1 and x2 and x3 and x4 up to xn, depending on how many variables that you have, they should all be 0. So it should be only 0 at the origin, nothing else. Okay. And in case you have this constant, we can always shift it and we solve the problem. Okay. So can we conclude that the downward position of the pendulum is stable? It is stable, but we cannot show with Lyapunov's direct method that it's asymptotically stable. And this is a little bit weird, right? We said that Lyapunov's indirect method is a weaker form of stability, right? We only do linearization. And using this weaker method, we concluded that the downward position, the downward pendulum position is asymptotically stable. When we tried the more powerful technique, which is Lyapunov's direct method, it failed to show us that what we already know, by the way. We already know that the downward position is asymptotically stable. But we only concluded that it's stable from the method and not asymptotically stable. What is the problem here? Is it the problem of the method? What? It's only the function that we chose, exactly. Now think of any other function and try to show that it is truly stable. What is the problem now? How many functions can I choose from? Infinite, right? So many functions that I can choose from. And this is the problem. So you see, the thing is this only for the pendulum? Again, you can show it in a very, very fancy way that all mechanical systems, when you start with this total energy, it will always have this problem. Okay? You will always cancel out the potential energy. They will always have no term here. Okay? If you have just potential energy, they will always disappear. And what you will always get is this term. And by the way, this also makes sense. What is the minus theta dot squared equal to? What is minus theta dot squared? What does it remind you of? First of all, physically, what is this system? It's a pendulum, right? It has potential energy, and it has what? Kinetic energy because it's moving. What else does it have? It has damping. In what sort? In friction in the joint, right? This term was only friction. We had here B over ml squared. So there was some damping here. So this B over ml squared, which what we chose to 1, in the end will be this term. So in the end, the rate of change of the kinetic energy plus the potential energy will be equal to the damping that we have in the system. This is, you can find this equation always. Whenever I took the total energy of a system and I take the time derivative of it, so the rate of change of the kinetic energy is equal to the power that's dissipated. So this is the power that's dissipated in the pendulum. You can always show it for all mechanical systems. And this is a problem. So again, I can give you so many examples on how Lyapunov theory works, but they are all toy problems. When you go to a real mechanical system, you're always going to get this result. And this is where Lassalle's invariance principle comes into place. So the invariant set theorem, or Lassalle's invariance principle, is an extension of this, of Lyapunov's direct method, to make it more useful for mechanical systems. Again, actually, I think we have, how much time we have more? 10 minutes. Okay, let's stop here. Okay, so that's just a motivation for next time. Okay, we don't have enough time. So any questions? No? Clear? Okay, let's keep it easy today. Next time, inshallah, it will be a little bit complicated.